Is the audio there? Okay. So any questions from last time? Last time's lecture should have probably been fairly straightforward. It's Reeve Takinagi's kind of geometric. You can, Okay. So today, we have kind of discussed IISc in various forms and also this entanglement related stuff. So now what we want to do is we are actually going to talk about the firewall paradoxes. So today's lecture is basically kind of an overview of what are sometimes called the various firewall paradoxes. Okay. So the claim. I already told you about the first firewall paradox, which is sort of done by Mathur. The idea of using this strong subadditivity in the context of strong subadditivity, or if you want to think of it in monogamy of entanglement, similar statements can be, you can rephrase these things in slightly different ways. So I'll talk in the language of monogamy of entanglement, but it's essentially a version of that can be formulated in terms of strong subadditivity of, as a violation of the strong subadditivity of entanglement entropy. Okay, so that language was used already by Mathur previously. So as I said, in some sense it was there for the taking since Page's argument was already there. So I would say that Page's argument is the biggest step after Hawking, and then Mathur made it sharp in terms of the strong subadditivity, and the final bit in some sense that AMS, Almairi, Marolf, Polchinski, Sully, their first firewall argument was basically using the fact that this can be made into a direct sort of contradiction the contradiction was also already there in some sense, but they made it as a precise statement about the late stages of black hole evolution. So that was the first firewall argument. So let me just call it the AMS paradox or Mathur-AMS paradox. Okay, so this is our first paradox for the day. And there the observation was basically that if you have entanglement entropy, so the shape is not very important. So this is the entanglement entropy and this is some time. And if you look at black holes after the Page time, which is basically here, so it's order m cube time scales. Okay, so you can roughly think of it as order s time scales. S and powers of s are not very important. What is important is the distinction between orders of s or orders of powers of s versus orders of e to the s or e to the orders of s. So those time scales are very distinct in qualitatively, and there are probably important distinctions between the resolutions of the paradox and paradoxes that, So there are versions of the paradox or the versions of the firewall that kick in at exponentially late times, which are basically in some sense, in my opinion, the strongest versions of the firewall paradox, which I don't think, it's not clear to me whether there is a way to resolve them. Okay, so in fact maybe the case is that at exponentially late times, black holes that are, like the large black hole in ADS, which lives for a long, are eternally there, and exponentially late times, I think that it is plausible that black holes have firewalls. Okay, so it is, so at least some constructions that I've seen, the arguments of Susskind, various things, all of them seem to make me think, it's my opinion, suspicion. I'm not super, in my papers I never commit to it, but even though there's a video, I'll say this is more committing than that. So, but I think it is plausible that at exponentially late times, black holes that are alive may have firewalls. Okay, so or at least we don't know any mechanisms that, in my opinion, it's not clear that it can be resolved. But so these firewalls that I will talk about, so I will talk about that. But the first firewall paradox that I'm talking about here, this is the original AMS paradox or Mathur-AMS paradox, and I think there are some quantum information people who had also come up with it independently after Mathur but before AMS. Okay, so So the statement here is sort of, I've already mentioned it once, but I'm just recapping so that we warm up for the other paradoxes before we get into it, is that, so at not exponentially late times, after the Page time, so most of the phase space is in the early radiation. Right, most of the black hole is mostly evaporated, so most of the radiation is in the far away. So that means that the new radiation that is being emitted, if the state has to be pure, it better be entangled to the early radiation. You know what I'm saying? And this is a statement that has nothing to do with black holes. It's a statement that has to be true for any burning coal or anything like that. So if you wait long enough, most of the stuff is far away. So whatever is happening now should better be entangled to the stuff over there. So that's just a basic fact about any kind of leaky system, roughly speaking. So that's the first statement. And the second statement, so let me call that, so let me draw a picture here. And let me introduce some sort of notation that is sort of standard, which is, I mean, this Penrose diagram is not really required. I mean, I can just, yeah, let me just draw a Penrose diagram actually. So, so this is some Cauchy slice, okay? So that goes like this. So this region is, sorry, this is sometimes called the Hilbert space A. This is Hilbert space, you know, so I forgot, I think this is called RB maybe. So I forgot what is a standard, you know, so this paper is from like almost 10 years now, 10 years ago. So this early radiation also had a name. Let me call it HR, okay? But I think there is a more canonical name might be there. So anyway, so the point is there is the modes that are interior, right at the, you know, at the right out in the interior, and the modes at the exterior. And the claim is that this B after, if this time is very late, this is after the page time, okay? So this is some clock that you have it near the boundary or something, so that this is like after the page time, okay? So so if that is the case, then the claim is that B better be maximally or near maximally entangled with HR. But then we also know from our own constructions that these two things have to be entangled with each other in a very, you know, maximally entangled in a very specific way for the horizon to be smooth. So these two statements together are in contradiction is basically the AMS paper's claim, the first AMS paper. Okay, so these papers are very long and they are very written in a qualitative way which is almost impenetrable in my opinion. So it's, but in the end this is what they're saying. Okay, so they're, you know, generally I found the AMS papers to be quite hard to read. Because even though there's no equations or anything, but it's very difficult to read, to navigate to what is going on. So, but this is the punchline. So, and this is what they're saying. So or at least, you know, this is what the consensus is, that that's what they're saying, and it seems like that's what they're saying. So this B and HR are entangled, and so these two entanglement statements immediately give you a contradiction. So our claim is the result is simple enough. Okay. So, and this is a statement for the evaporating black hole. Okay, and so the AMS, the firewall or AMS suggestion was, as I said in one of the first lectures where I said this, is that maybe the conservative thing is to sacrifice the entanglement between B and A and declare that this is basically there is a firewall. Okay, so then of course there is a question, yeah, okay, let me not get into that. So this is, so the current, let's say, consensus is that it's probably more natural to say that A and HR are the same system, or more, you know, more fancy way of saying nowadays is that A is in the entanglement wedge of HR. It essentially, entanglement wedge is just a statement that these degrees of freedom can reconstruct this. That's all it really means for our purposes, okay? So if that is the case, we have sort of resolved the paradox. Okay, so of course the challenge is to really implement it explicitly in some controlled model, and there are some toy models where people can do these things. I think as for instance Apurva has you know, some papers that he has looked at. So those are kind of toy models. We don't have full control on like a full quantum field theory setting. We don't know how to, quantum field theory or gravity kind of setting, we don't know how to do that, but it's also not really necessary. We just need to construct a toy model where the contradiction exists and then resolve it in the toy model. Then we at least know in principle this is the idea that is good enough to resolve it. Okay, and that's what there are some these papers on non-isometric codes, etc. that are recently, you can, you know. So now of course, I mean, I'm going to be more talking about things which are current. So it will not be a complete description of various words that I will use. I will not be able to fully discuss. Okay, but this is the statement. So there are models where we seem to be able to resolve these issues in the context of an evaporating black hole. Yeah. So that's the claim. Yeah. So that's a sorry. Cloning is, so the statement is not that you started with the state and made two copies of the same state without doing anything else. That's not the statement. The statement is that this state is the same thing as this state. It is not that there are two copies of the same state sitting here and here. So this state basically encodes this state in some you know, holographic way. Okay, so this is some kind of extreme version of holography. And yeah, as I think I mentioned it last time, so it's, you know, at least it makes you think about holography. Okay, it is, in some ways it is different from holography, but it makes you, it's really kind of like that, right? So this is some bulk region which seems to be encoded in the degrees of freedom sitting here, the early radiation. So this is the claim, yeah.
So does it mean that after the page time, all the information that is in A actually suddenly appears in the radiation? Is it that received from A and appears in the radiation?
It's not so much that the information appears. You can phrase it in the language of what is called quantum teleportation. You can phrase it in the language of that in some ways if you do some measurement, etc. But here I'm just saying that this Hilbert space is the same as this Hilbert space. How exactly it happens, I've not told you. Okay?
But after the page time, you are saying there is a sudden firewall.
So the firewall argument becomes strong only at that time.
Yeah.
Okay, so the firewall argument becomes important only at that time. So see, the point is that, how did we get here? We got here basically because we were approximating the initial evolution of entanglement entropy by the thermal entropy of the radiation and the final evolution of the entanglement entropy with the thermal entropy of the black hole. So that's how we are getting the page curve. Okay, so in both cases we are computing thermal entropies, but we are using those thermal entropies to make statements about about the entanglement entropy of the system. So I don't know whether I think you're so I don't know, maybe I didn't answer the question. You can ask again.
But from this page curve, it seems like that after the page time, entanglement entropy decreases, there is information that is in a system A, and it is coming out from the black hole and
See, it's a statement about how the entropy changes, right? There is an evolution in the entropy changes, but it's not really saying anything about suddenly. There is no firewall is the claim. The firewall is never there because the reason why A becomes reconstructible from HR is to avoid the firewall. It doesn't have to be, I mean, the suddenness is not sort of the point. There is no, first of all, there is no sudden appearance, there is no firewall anyway. So there is no notion of suddenness of the appearance of the firewall. So what I think you mean is that there is a phase transition happening in going from here to here. So that is essentially like, there are various ways to understand it. But here, the observation is that there is a change in the way, for instance, how we are computing the entanglement entropy here. So here note that in this kind of a black hole this is basically just a calculation that is purely, as I said, there are 2 or 3 ingredients in it. One is that this is the assumption that this is a pure state. Okay, so the assumption that this is pure state is crucial, and that's the assumption that Hawking sacrifices, because when he uses the untrue state in order to predict the thermal radiation at all times, he is stuck on this line forever. Okay, so but we assume that there is a pure state, some unknown pure state which we don't know anything about, and then you make this assumption about how the entanglement entropy changes at early times and late times, then you get the page curve. Okay, so that's what is being done there. So, but on the other hand, we don't know what is the mechanism for the retention of the pure state, because Hawking's calculation we used a thermal state. That's untrue state. That's how we computed it, right? So that doesn't mean that. So this is kind of like a hope and a prayer kind of calculation. What Page did, which is that let's assume that the state is pure throughout, which is just that it is somehow being simulated by a thermal state at the time of radiation from the horizon. But let's assume that somehow there is an underlying pure state, some complicated pure state which we don't know anything about. So if that is the case, then the page curve should go like this. So this is the observation. So and that same assumption here, how exactly is the mechanism of how that entanglement is, I have not told you, and there is a story there. Okay, so this A is how is it being reconstructed from HR is a story. So that we are not discussing now. Maybe we'll have time to discuss it, I think, but so that we will come to eventually. So the structure is analogous. It is just basically A is engineered to be reconstructed from HR so that there is no firewall. So there is no question of firewall suddenly appearing at page time in this, if this logic is correct. Okay. So yeah, any other questions?
So continuation of this, there is no firewall in this, right? So
yeah, if A is in the entanglement wedge of HR, there is no firewall. Right. So that's the statement. Any other question? So I was just recapping this so that you're kind of in the same headspace. So as and now we are going to talk about the other firewall arguments. So there are 2 or 3 firewall arguments which have come up in the last decade or so, which I think are, kind of discussed. And the next one I'm going to talk about is, in my opinion, the strongest one, and I don't really know of a convincing argument against it. Okay, but you will see that there are various approximate slash. You will see that you have to make some assumptions. None of these things are very easy to make completely watertight. And in my opinion, all of these problems are really to do with our ignorance of the Largen limit. That's really where all of the problems are coming. If you can make the Largen limit very precise and clean, I think that all of these things will resolve themselves, is what I suspect. Okay? Or we will know where the firewalls are. So, but here the problem is, most of the time, Largen limit is just a phrase that people like to throw around, but it's not completely under control. So Largen limit means n has gone to infinity. But whenever you send something to infinity, you have to define how exactly the other quantities in the system are being scaled. Otherwise, it's not a well-defined limit. So while people can use that phrase, it is not completely clear how that limit is being taken. Okay? So, and that's where a lot of these problems are happening. And I think that the recent developments of, for instance, Leuthäuser and Liu is kind of an indication that that's going to be very crucial in understanding these problems very well. Okay, so anyway, so the second paradox, the one that, so this is what I think it's called the typical state firewall paradox. So this is probably the strongest one, and which we don't, it's not clear to me completely, as I said, how to resolve it in a completely satisfactory way. So so this is the second paradox, and this was first formulated by Marolf-Wall. Okay, so yeah, I'm roughly speaking again following Harlow. Okay, so even though I think his discussion, I'm clarifying it a little bit, etc., etc. So, and also trying to emphasize the places where the assumptions are, I think, are assumptions. Okay, so there are places where I think it's not completely clear the end dependence of various things in my view. So the assumptions that we make, I'll just try to emphasize. It might be that there are people in the community who know these assumptions better, but I suspect that these things are vague at the moment. Okay, so so yeah, let's look at, so typical state firewall is sort of precise in the sense that it's a statement about the eternal black hole in ADS. An eternal black hole in ADS, if it is sufficiently high energetic states in the CFT, we expect that these things are black holes. That these are eternally there. So, and they are eigenstates, or at least they are in the microcanonical sliver of CFT states, heavy CFT states. This is the expectation. So I don't really need to do the, so eternal black hole here, I'm not really trying to emphasize the double-sided picture. I'm just trying to say that these are large ADS black holes which are stable in the microcanonical ensemble. Okay, so that's what I mean. So let me not draw the picture of this. But so the thing would be, I'm just mostly interested in this edge of that. Okay, so this is the future. So if you want, I'm drawing it, looking at this region. Okay, so I'm focusing on it. So here I again have an A region and a B region. Okay, so the A is the interior, and B is the the exterior part. Actually, let me make it this so that I can motivate something. So, yeah, so I'll draw it like this. Okay, so the point is that, so this, so if you have, let's say, operators, so you want to look at, so you are looking at bulk effective field theory. Okay, so bulk effective field theory means gravity with fixed backgrounds, maybe with fluctuations, or not necessarily fixed backgrounds, but with gravitational effective field theory in the bulk. Okay, so which means scalar fields and gravity, but we don't necessarily claim to know what the UV completion of the theory is in the bulk. So that's what bulk effective field theory means. So, so let's say you have a scalar field in the bulk, or any mode in the bulk. Okay, so and that you look at from the extrapolated dictionary which we wrote down. We expect that there is some dual O sitting on this other side, in the boundary. So this is in the boundary, so there is some operator here. And this is also the paradox where ADS-CFT is really required. Okay, in order to frame this paradox. Note that I did not use ADS-CFT to make that paradox. I just basically made it just based on entanglement and evaporating black holes and all. But here, I get a sharp paradox because of ADS-CFT, and ADS-CFT is crucial. So, and probably because of that, it is also not very easy to resolve. So, Yeah, so this is, you can think of these as single trace operators or generalized free fields. This is what you generally imagine, right? So, and the point is that if you have an expansion like this, you can also, if you have a phi going to this kind of thing, you can also do a Fourier expansion here, the mode expansion of A and A dagger if you like, and then they will also map correspondingly to the A and A dagger here. Okay, so because the bulk guy basically, so the information in the bulk is sort of trivial. So what it is really saying is that there is a particular mode, so usually labeled by energy and angular momentum quantum numbers on the boundary. Okay, so this is essentially some mode A, let me call it A. Okay, so these are, you can think of them as the mode expansion of phi or of O. Okay, there exists some mode like that, and there will also be some creation operator A omega Lm. A dagger omega Lm. Okay, so the point is that, so the first observation that I want you to notice is that if you are expanding fields in this region, in the region 1 of the Kruskal coordinates, it's basically like, you should think of always an analogy with Rindler or Schwarzschild. So we are working either in Schwarzschild coordinates or Schwarzschild ADS more precisely, in Schwarzschild ADS coordinates, or we are, as an analogy you can keep in mind Rindler. So the point is that, so this guy we can compute a number operator, which is, let's call it the boundary number operator, which is A dagger omega Lm, A omega Lm. This is something we can just do, right? So the point is, and the reason why we can do that is because note that I have used the large N limit here. Because generalized free fields, so the idea that the small fluctuations around the black hole can be approximated by free fields is part of the assumption. Okay, so that's why I expanded it in terms of free modes. Phi I'm assuming that phi can be expanded in free modes, and then if they are free modes, I can do this. So note that the large N limit has gone into this statement. Without the large N limit, you cannot make this argument precise. Okay, so the existence of these small fluctuations around fixed backgrounds is essential sort of to make the following argument. Okay, so this is my number operator, and in large N limit this is true only up to order 1 over n corrections. Okay, but I'm not going to keep the order 1 over n corrections super precise, because I think the precise limit in which this argument holds I don't think is understood. So I don't think it is very meaningful to keep track of all the order 1 over n type of stuff. Okay, so anyway, so let me just, so that's my number operator, and so this number operator, now the key point about this number operator is that this commutes with the HCFT. Why? Because the time coordinate here is the extrapolate time coordinate on the boundary. So if you have a time coordinate in the bulk here, this time coordinate can be mapped onto the boundary, because it is just, you expand it in the standard ADS. Let's imagine ADS. Schwarzschild is also the same way. So if you have ADS in cylindrical, or what is that? The ADS cylinder coordinates, or the global coordinates, then the time coordinate on the boundary and the time coordinate on the bulk are the same. And that's true for Schwarzschild as well. Okay, but not inside the interior. But everywhere outside the horizon, the Schwarzschild time coordinate, I mean, this is just basically the metric that I wrote down last time, right? So this, some metric stuff, plus this, dr square by whatever, plus r square d omega square. Okay, so this is my ADS Schwarzschild metric. And I'm saying that in the r going to infinity limit, or r in some large limit, this guy is basically, this time is the boundary time coordinate. So because of which we expect that sort of a statement is true. Okay, so the number operator here, because this is just expanded in the positive energy modes in the bulk, but that bulk time and the boundary time are the same. Okay, so this means, what does this statement mean? This statement basically means that we can, so we can diagonalize the spectrum of the Hamiltonian in this microcanonical sliver in terms of this basis of number operator basis. Okay, so that's the observation. That's what this buys you. Note that this, so you might think that, so all of the things that I'm saying here are actually true. So now I'm going to say some things. All of those things actually, you could have said many of those things, both in Rindler and Minkowski as well. So, but none of them rise to a sharp contradiction, because there is no bulk to boundary map. We don't have a boundary Hamiltonian there. Okay, so this is where radius safety goes in a crucial way. Okay, so. It doesn't matter, right? So this is here, what we are talking about is some large heavy black hole. In that background, we are computing the mode expansion in some coordinate, some time. So that time is, so once you know, the fluctuations around a given background is where the time is going in. Right? So that, those fluctuations are, you know, so that one could make these questions more precise and talk about how exactly one should think about these limits. This is, in some sense, your question is related to the question of how you take the largen limit. Because how do you treat the back reactions carefully if you have, like, you know, these modes? So, but I would say that, like, but the problem is really, you know, as long as we have the notion of a black hole, the boundary time can be used to define the notion of positive energy modes in the bulk. And those modes are precisely the ones which become the Schwarzschild modes, or in the analog of Rindler modes, in the context of basically they are the analog of Rindler modes. Essentially, the point is that we are going to use the fact that the CFT time is an analog of the Rindler time. That's what we are going to do. And then we are going to find an argument for why that is problematic with the Kruskal time here.
At the boundary, like single time.
Yeah, so but I'm saying that is that time can be used. Whatever else you do, they will be trivial diffeomorphisms. So this is the time that you have to respect, is the point. So that time is all that is required in order to define these modes. And once you define those modes, whatever else you do, you can do various things. So none of them will affect this argument, because these modes which are defined at the boundary are what you need in order to write down bulk fields anyway. So whatever else you do, they will change things suitably inside the bulk, but the argument will remain the same in terms of those new guys. So it doesn't matter. Okay, so yeah, you can do various trivial bulk diffeomorphisms. So, but those will not change the issue. So the only diffeomorphisms that will be important will be, you know, and this is what the part which is not fully understood still, is what happens if you do a diffeomorphism which does not vanish at infinity, so that the time translation at infinity, infinity means that the boundary can actually, you know, it can move the boundary time. So that's really a genuine time evolution in the CFT. Right? So that's not the same thing as a bulk diffeomorphism which vanishes at infinity, which is a trivial diffeomorphism. So that doesn't matter. Okay? So so that's what we have. So this gives us, so this suggests that there exists a complete basis of eigenstates of NB which span the microcanonical ensemble. Microcanonical ensemble. So I mean, all of the questions, you might have many questions about various statements, and all of them are, I think, one should think about them. But I don't think it is completely clear. This is a quasi, still I would say at the end of the day, this is still a quasi heuristic argument. You know, it's not like, but I think in order to fully resolve it, I think we'll have to be careful about how n is going to infinity and how we are keeping all these states. You know, because the single trace sector, basically, a single trace sector means these low, small fluctuations around them. You know, how, you know, so it's clear in some sense that n going to infinity will be important, because if the scaling dimensions are very large, it will start back reacting. Right? So those kinds of things one has to worry about. So I don't know whether it has been fully, cleanly ironed out. But anyway, so that's what so this is the claim. Let's make it as the claim. If you are, there exists a complete basis of eigenstates of NB which span the microcanonical ensemble, or some microcanonical sliver. Okay, some fixed energy with some, some small delta energy band, if you like. So in that band, you can span it using this. Okay, so now the second piece of the argument. So now we use the A system. Okay, so the A system, so the point is that, so note that this A system, so these B's basically are coming from basically these modes which are going like this. These are what we call outgoing modes. So ingoing modes you can think of as the modes that were going here, but sort of analytically continued into the interior. Okay, so this is the same thing that we have actually done when we did Rindler to Minkowski. So there also we needed the left modes, the left Rindler modes, in order to construct the modes everywhere in Minkowski space. Okay, so that's essentially the same idea. So the point is that the left guys, the left wedge guys are what we need in order to construct a smooth patch of space-time here in terms of, and that's what goes into A. Okay, so the A, what it carries is basically A, what you really mean by A are these left movers. That's what you really mean. Okay, and you need both of them in order to construct a smooth horizon, and one example of that is sitting right here when we do Minkowski space. Okay, we need left and right. And so let me call A tilde omega Lm as the modes that are defined on the interior here. Okay, so they should exist if I have to have a smooth horizon. So if I don't assume that, then I already have a firewall. Okay, so if I assume that A tilde is something that exists, which is entangled in some suitable way, etc., is what we want. So now if you grant me A tilde omega Lm, I can construct the analog of the Minkowski vacuum, Minkowski modes. So the Minkowski modes were defined in terms of this C omega Lm, if you remember. All of these I wrote down there. I am not going to write down the normalization now. So there is 1 by 1 minus e to the minus 2 beta square root or something that I wrote down at the time, but it doesn't matter. So, but the point, crucial point is that this is the structure that it will have. This is not C, this is A, and this is A tilde dagger omega Lm. Okay, so this is essentially what is this. So this is you can think of as this thing is something you can think of it as a Minkowski mode, Minkowski-like mode because we are working with a black hole, Minkowski-like annihilation creation operator, annihilation op, or Kruskal, or sometimes people also call it the infalling mode operators, infalling ops. Okay, so all of these are the same thing. Okay, so Kruskal is sort of like a proxy for the infalling coordinate, infalling modes. So this is the structure that you will have. This is what you expect. Okay. So now what is the expectation? So the expectation is that if you want a smooth horizon, a number of operators constructed from this should smooth horizon. If this is a state with smooth horizon, this should basically be 0. Is that clear? Basically the point is that you should not see any excitations if you are in the vacuum state or some smooth state like Kruskal state. Okay? So you should expect that number operator will be basically because C annihilates the vacuum there. Okay? So this is what you would expect. But so this is essentially but if you break the entanglement structure here, which is another way of saying there is firewall there, then this guy, if it is non-smooth horizon, so C dagger C on, so I should be a little bit more careful. I'm not being super clean here, because if you remember in the other class we introduced 2 sets of modes, C and C1 and C2, because essentially the point is that the left modes here and the right modes here combine together to give you a complete set on the entire Cauchy slice. So you need 2 copies, very roughly speaking, because otherwise if you just use this guy, it's kind of like it's only like half the set of modes, very roughly. Okay, so you needed 2 of them because we have introduced A and A tilde. So then there is A dagger and A tilde dagger. So all of them have to be combined into this 2 sets of modes, and these 2, let me call actually this one C1 or C1 omega Lm, and there will also be a C2 omega Lm, and then there are Hermitian conjugates. So that's the structure, but it doesn't matter for my discussion. There will also be instead of C dagger C, you'll have C1 dagger C, this thing annihilates, and also C2 dagger C, C2 annihilates. That's all. Doesn't matter. So that's why I'm only talking about one guy. So yeah, so this should annihilate. So this will not be 0 if you have a firewall. These are firewall states. So these are the 2 kinds of states that we will distinguish. Okay, so some states, whatever states they might be in CFT, so you would expect that they can be constructed in this way. Okay, so this is the statement that we expect for a system with a smooth horizon, and system or a state with a smooth horizon and a state without a smooth horizon. So these are what we would expect. Note that I'm phrasing it in terms of this A tilde or on the left CFT for convenience, but really you always, as long as you have a smooth horizon, you expect that there should be left movers there. That's essentially the condition for the smoothness of the horizon. So, and that's how we, for instance, we have, discussed this before. So, essentially that's, it has to be, so how exactly it emerges, for instance, in the context of, for instance, an eternal black hole and CFT, etc. Well, that's another discussion. But this statement is basically something that we expect anyway. Okay, so even though in this picture I'm motivating you through this eternal black hole picture, you should not think that this question is limited to that. This is more like it's a statement about the existence of this operator. If this operator doesn't exist, then you already have a firewall. Okay, so I'm motivating it using eternal black hole, but this should exist if there is a smooth horizon. So so then that's the statement. So now, but the thing is, we have. So now the final piece is that if you have, let's say, but C dagger C acting on any of these NB eigenstates is always order 1. Why is that? Because these NBs are really like Rindler modes, right? So Rindler modes are basically always have firewalls. Rindler modes have only one side. So that means essentially that you can actually check it explicitly also if you like. You take this and you act on the Rindler half, you will find that it is not, it's not identically 0. So this is basically what defines the Minkowski vacuum. Okay, the Minkowski, this operator annihilates the Minkowski vacuum, but it is not going to annihilate typically any of the other states. In particular, the Rindler modes. Okay, so that's why this is something that we don't care what it is, but it's definitely not 0. It's some order 1, whatever number. Okay, so this is the reason why this we expect. And since we have argued that this thing can span the entire microcanonical sliver, right? So what we have identified is that we have identified a set of basis states for the microcanonical sliver, for all of which have firewalls. That's what we have identified here. Okay, so this is not yet a statement about the typical state in the microcanonical ensemble, but we can go from there very easily. I'll tell you in a second. But right now what I'm saying is that any eigenstate in the microcanonical ensemble of NB, so there is a complete span of the microcanonical ensemble. There is a basis that completely spans the microcanonical ensemble, all of which have firewalls. This is what we have shown. And from here to argue that, what we want to say is that, okay, so from here, if you compute the average over the entire microcanonical ensemble, obviously it will be order 1. Right? So, but then there is another statement which is also something I mentioned previously, which is that typical states have correlation functions which are exponentially close to the average in the ensemble. Okay, so if you compute the average in its order 1, typical states in that Hilbert space will also have order 1 up to exponentially small corrections. Okay, so that shows that typical states in the microcanonical Hilbert space have firewalls. So this is, there are various places one could question some of these things, but I think that you can go and think about it. Okay, so the general story is this is how it is framed. So whatever is not convincing, you can think about it. Okay, so yeah, let me just walk you through one more time through that. So the first observation is, if you have this single trace, small fluctuations around black holes are basically captured by the single trace operators or generalized free fields. So there is a free field expansion for it. So they have mode functions, and these mode these mode operators, and these mode operators, and this is where ADS-CFT goes in. You can extrapolate to the boundary, and they define a number operator on the boundary, and because the times are the same in the bulk and the boundary, we expect that these two should commute. Okay, so this means that in the microcanonical sliver, we should be able to construct a basis from those eigenstates of the number operator. And if you have that, then because of the fact that the Minkowski modes, or the Rindler, or the Kruskal modes, or whichever modes have a smooth horizon, will not annihilate them, right? Those guys are basically constructed from the Rindler time, or the analog of the Rindler time. So, and they are definitely not going to be annihilated by this by construction. Okay, so all the states in that basis of the microcanonical ensemble have firewalls, and then by typical states and the average, typical states are arbitrarily close to or exponentially close to the average, we can argue that typical states also have firewalls. So that's the chain of logic. So, and this I think is, even though there are various places where there are, it's not a completely watertight argument and it's hard to make it precise, but I think trying to make it precise is a worthwhile enterprise. Because I think it will force you to kind of make n going to infinity a precise statement, and how various states, what kind of states in phi should one keep, etc., etc. My prejudice at the moment, and it has changed many times in the past, so I cannot really vouch for it, is that typical states probably have firewalls. Okay, so but yeah, so I have never said that in a paper very confidently. But at the same time, I think there is many, so this is, it's not me who is saying it for the first time. Other people have also said it. But the point is that I would say that the evidence for it is slowly mounting. Or at the very least, let me put it this way. I think the states, which are not typical, it's clear why they will be smooth. Their horizon will be smooth. I think there are good reasons to think that for various, as already I said, some of those reasons, there are some. But here it is not very clear how we can get out of this kind of an argument. If there is a way to get out of an argument, one should make it precise. That's the statement. And I suspect that it is hard to do that. So it looks somehow like, there is not enough room in yeah, so okay, I'll make more comments about it as we go. Yeah.
At CFT, the Hamiltonian on the left right.
So you should not think of, as I said, this is, you should really, this A is there, this is the reason why initially I didn't draw it. You should not think of it as a statement about two entangled CFTs. It is kind of a way to motivate these A modes. That's what this is. So in some sense, whenever you replace a thermal state with a thermophile double, the understanding is that you're somehow replacing the fine-grained information that you're ignoring in the thermal state with some purification. That's the way to think about it. So these A's, for instance, they are like, they are coming from some complicated information in the CFT which purifies the state, for which we have put a thermophile double proxy. So that's the sort of the way to think about it. So thermal state is basically some state which has a lot of, coarse, fine-grained information which we are ignoring in some sense, right? So that fine-grained information is basically, it's a proxy for that. So if you kept track of all the fine-grained information in a thermal state, the state will become pure. It will no longer be a thermal state. Okay? So yeah, so that's the idea.
My question is like, so in the large, in the attention side, so you cannot write this error expression to the tensor product of the pattern.
In the large n limit, we cannot write this into this sort of thing.
Yeah, tensor product of the left limit space and the right limit space.
No, I think the question is what is, so then in the large n limit is where we expect it to have that form, right? Because the point is that this is the place where classical gravity sort of, we expect it to be believable. Because so n going to infinity is in some sense close enough to gravity, right? Classical gravity. So that means that in this state, which is basically a so this picture, the classical picture of Kruskal diagrams, etc., should make sense. So, but the point is that we don't fully understand how to take that limit very well. N going to infinity limit. So these are, most of the time we are talking in somewhat heuristic terms. And that's part of the problem. So what kind of states are you retaining when you send n going to infinity, etc., are the question. So here, for instance, there is roughly the picture that seems to be emerging is that there is some heavy state and its fluctuations around it. So the idea is that you're sending n to infinity while holding a quantity called complexity fixed. Complexity of the state fixed. So this is roughly what I think it is. Right now, I think that's where it is headed. So this is like what very recent development. So we will, So I'm just, this is like stuff from 2013 or 12 or something. Okay, so almost 10 years ago. So that's the Marolf. So this is not Marolf-Wall. Sorry, I meant Marolf-Wolczynski.
So this Hamiltonian actually, we can say that it do some time evolution.
Right, yeah, so the boundary, so the point is that outside the horizon, there always exists a time coordinate that can be extrapolated to the boundary. So you can do further diffeomorphisms on it, but they don't add anything. You can make the statements in terms of them if you like, but doesn't add anything. So the bulk diffeomorphisms on top of that time are not really doing anything new.
So this time dimension, I mean this Hamiltonian corresponding to that dimension that.
Which Hamiltonian? There's only one Hamiltonian here, the CFT Hamiltonian. Yeah.
That's CFT, and this is taking us inside the OL.
No. So this statement, I did not justify this A tilde omega LM other than by the demand that if I want to have smooth horizon, I better have this. Okay, so but then if I have it, then I can construct this guy and then I can find another contradiction. So either way, if I don't assume it anyway, I have firewalls, but if I assume it, I can show that the typical states will have firewalls. Okay, so this guy, I'm not really at the moment, I'm not explaining what is its origin in the CFT. But roughly speaking, because thermal states, as I said, are like kind of only retaining the coarse-grained information, these guys should roughly correspond to some fine-grained information in the CFT, in a single-sided CFT, which we are ignoring. Right? So this whole thing is a picture that is supposed to be like a proxy for a thermal state in a single CFT. Right? Thermal state is there is no truly thermal state, right? A thermal state is always an approximation. So let's say you prepared some heavy state and you let it evolve, and it basically evolves and becomes more and more thermal. So at some stage, it when you choose to ignore certain coarse-grained information, that basically looks like a thermal state, and you can write a purification for it, which is of this form. And this is useful for various purposes, and there is good reason to think that it captures some real physics. So the question is, but what is that approximation under which the thermophile double approximation matters? So, and the claim would be that since only this side is really the the stuff that is accessible in terms of single trace operators and simple fluctuations around it, the natural guess is that this is some sort of fine-grained information that we have ignored. That's what does this. But why does a holographic CFT, when it thermalizes, have this fine-grained information organized in this particular way that it has interpretation as a smooth horizon in some holographic geometry? That's really the puzzle. So this A is the idea would be that this is a proxy for some fine-grained information. That's the way to understand it. But the interesting thing is that for black holes, so typically we don't even care about this fine-grained information in thermalizing systems, because fine-grained information is gone. But the remarkable thing about gravity is that in this large kind of theories with holographic duals, this fine-grained information seems to allow this interpretation in terms of a smooth horizon. So that's the real question, and I think that we will have to understand it in some meaningful way before we claim that this information paradox is solved, because I don't think we have understood it. So in large theories, why is it that the fine-grained information under dynamical evolution organize itself in this particular interesting way? So that's the real question, and I don't think we understand it. So we have made progress, in terms of this, what is it called? The quantum extremal surfaces and islands and all that. So there are various things we have made progress on, but none of them really have completely understood it, but it's progress. Certainly it's progress, I think. So because it is making a statement about the interior of the black hole, those things. So in that, because there is some structure that we have identified, which seems to be relevant for it. So clearly it must have something to do with understanding these things, but I don't think it is yet clear. Okay, so any questions? So once we have it on a general basis, then we have it also on the typical states. So so this is sort of, in my view, if we can really completely understand this paradox, I think at least in ADS-CFT we would have understood information paradox quite well. But that's, there are many pieces there which I think have to be understood well. Okay, so this is the typical state firewall. So now let's go to some other, more so now let's talk about another. There are three papers which are basically sort of famous in the context of firewall. One is the AM's original paper. Then there is another paper which I haven't yet discussed, which is called I think this is Stanford now. Okay, so there is one more author, and that's a second paper in the list, and that's the third one. Okay, I went slightly non-chronologically. So this is the second paper, and this I'm now going to talk about this paradox. Okay, so I'm just basically going through the paradoxes that Harlow has listed. So I mean, but these are standard paradoxes, but there are various. I mean, there are other paradoxes also one can come up with. Maybe we'll talk about them also because some of them are interesting. So, for instance, there is a paradox called the bags of gold paradox, which I think also is kind of interesting, and it's not quite the same thing as this. So, but yeah, let's talk about the ones that Harlow is talking about. Okay. So, so this AMPS paradox is again. So this is basically the idea is that okay. So this So this picture is already here. So let me just use it. So we know that, so there is these operators A sitting here, and we expect that there is A dagger and A tilde dagger. Right? So this is what we expect. So the question would be, so now the thing is that we know that, so the first observation is, so what is, it's again a kind of like, what are the natural properties that one can expect for these A tilde operators in the CFT? Okay, partially motivated by our understanding of the eternal black hole and Minkowski-Rindler connection. So one of the things that we would expect is that we know that these modes, this A tilde and A tilde dagger, are coming from the left wedge. They are basically just the same modes as here, but on this left wedge. Right? I just drew it on the, I'm just using them to construct the interior. Because once I have this guy and this guy, everything is constructible by that combination of this Minkowski-like mode that I wrote down. Okay, so the point is, but the interesting point is that we know that, so on this side, this time here is the analog of the Rindler time, and that's the analog of the CFT time. Okay, and so naturally here there is another time going this way. So this time, so this A and A dagger, basically A races in some sense. So if you think of, if you do a single boost operation, right, the time here will go backward and the time here will go forward. So it's natural to expect that A tilde will actually, is the operator which raises energy, and A tilde dagger lowers energy. Okay, it's a natural thing to assume that's what it does. Okay, so and if you do that, so that's our first assumption. I mean, you can say that these are like, these are expectations. It's not like it's to say that I wouldn't, if you really try to sharpen it to the point of a real paradox, I think you will solve the problem. You know what I'm saying? So this is somewhat heuristic, as you can see, because I mean we are not able to explicitly construct these kinds of operators, which are basically about the fine-grained information in the CFT from first principles, because it's a strongly coupled large and gauge theory, and it's thermalizing. We don't even know how thermalization works in simple systems. Okay, I mean fairly simple systems we know, but so that means that these fine-grained information is very hard to keep track of. So that's what we would really need to make a very precise statement about it, or some other clever idea. At least frontally, this is what you have to do. Okay, so that means, so this statement you should not take it as like some sort of a watertight statement, but it's more like plausible heuristics. So this A tilde dagger lowers CFT energy. Okay, that's the first observation. And so that's, let me just make it into a first observation. And the second observation is that because it is a dagger in bulk EFT, we don't expect that it will be able to annihilate any states. Okay, so in bulk EFT, which presumably has a CFT duo, A tilde dagger cannot annihilate or does not annihilate states. Okay, so now let's assume that both these statements are true in the CFT, then we run into a contradiction. And the reason why there's a contradiction is because A tilde dagger is lowering energy in the system, so you're going closer and closer to the vacuum. So you cannot go arbitrarily negative. So somewhere we have to annihilate something. So that leads to a contradiction between this and this. So this cannot both be true in the same time. So this is, again, you can see that it is, it's a paradox only to the extent that you believe these statements. You know what I'm saying? So, but these are plausible heuristics, and this is sometimes called the AMPS paradox. AMPS, double S paradox. Okay? So now we have covered basically everything that AMPS and their collaborators said during those couple of years. Okay, so these are the three paradoxes. And then I will tell you about, what is the time now? Yeah, so, what should they arise. Yeah. So I'll tell you about what is called the Marolf-Wall paradox. Okay, so this actually has become a bit interesting in light of this Lloyd-Oyster-Liu results. So let's talk about Marolf-Wall paradox. So Marolf-Wall paradox is, I mean, again, this is, it's whether it is really sharp enough to call it a paradox is one has to see. But the idea is basically this really relies on the eternal black hole. Okay, so note that all the things that I said so far, they basically rely on the smoothness of the horizon. And you assume that there is something that should work like the tilde operators. That's what we are really assuming. We don't really need an eternal black hole to make that statement. As long as the heavy state is stable in this, then it is fine. By the way, this is also an eternal black hole paradox. Okay, so you have to distinguish between the paradoxes. So the first Am's paradox was for an evaporating black hole. This is for an eternal black hole in ADS. Okay, and the typical state firewall is also for an eternal black hole in ADS. So those are the things. So okay, so let's now we are again going to talk about eternal black hole means I'm not necessarily assuming thermophile double. Eternal black hole I just mean like a state which is heavy enough so that it is there, it is always there. So but if you assume the thermophile double picture, then you can make this Marolf-Wall paradox. I mean, I think versions of this I have heard Mathur say it also. So I don't know whether it is maybe he said it later, but clearly he was not a fan of this eternal black hole construction for a long time. So it's usually attributed to Marolf-Wall. So the idea here is basically this. Let's say that you will consider the thermophile double. Okay, so and you act on the thermophile double with some operator. Let's call it EIOL. Okay, so this is my state, some new state psi I will get. Okay, where OL is an operator on the left side. Right. So this state. Now, the point is that we expect, because of the causal structure of the bulk, that if you act with a right side operator, OR here, so this should be equal to okay, so this is something that we expect. Why? Because whatever you do here, it's causal, the future influence is going to be inside here. Okay, and this guy, this cannot be affected by that. So it's out. Nothing that you do here can really be affected by anything that happens here. So from causal structure, if you believe the bulk causal structure, this should be true. Okay, so note that this is a bulk argument. It's not a directly CFT argument. So, but if this is true in the bulk, then this has to be true somehow in the CFT, right? So this is from bulk causal structure. All right, so where are we? Okay, so the point is, so this is, you could say that, but on the other hand, from the CFT side, so in other words, what it means is that, but also on the other hand, you can also look that, let's say you send something in from here, and let's say you send something in from here. From the bulk point of view, in principle, they can have interactions. Right? So there is some interaction that is happening in the bulk of the CFT, bulk of the space-time, which seems to be somehow described in terms of, we need a better way of, we need to have a way of describing it. It's not clear how it happens. Okay? So essentially what it is saying is that if you want to describe the time evolution in the interior of the black hole, then you need to have some notion of, this fine-grained information that you wants to keep track of when a state thermalizes. Okay, so if you want to discuss this from a single-sided black hole, let's say a thermal state, heavy state in the CFT, and some heavy state in the CFT which looks like a black hole. Heavy states, as I argued earlier, generic states in the CFT which are heavy, they look like large black holes. So let's say you add some single trace operator on the boundary of such a black hole space-time, then how are we going to? So there is no explicit left Hilbert space. Right? So somehow you will need to understand this information in terms of the fine-grained information. Okay, so so this is sometimes called the Marolf-Wall paradox. I mean, it's a paradox to the extent that there is something, how are we going to explain the interior if from this, if you just had a right-sided CFT? How are we going to do that? So this is again kind of suggestive in some sense. So one way to say that it is maybe it's like a contradiction is because it is a contradiction. I mean, it is a contradiction in the sense that if you want to explain the black hole interior from one side, it's not very clear how this should be made sense of. And the answer to that is like, again, this was recently shown in some sense that the confusions are all in the large n limit. So I'm not going to say what the resolutions etc. are, but I think that's one statement I'll just make. So this is a paper by Leutheuser and Liu. Okay, so so let me say a few words about I'll maybe elaborate on it more later, so I'll just say a couple of things. So the general idea, so it's kind of related to this eternal black hole discussion that we had so far. So the idea is that how are we going to understand, so the black hole interior, how are we going to understand in terms of so let me define a quantity called complexity. So I'll be somewhat heuristic because the idea itself is a little bit heuristic, but I think it is an important idea which will play a role in the future. So most of the things that I'm saying were said by Susskind. Okay, so in many cases you will see that Susskind is often 2 steps ahead of, even though he's 85. It's like, it's surprising. So so the complexity is basically the idea that, see, there is time dependence in the black hole interior, right? If you have an eternal black hole, a geometry like this, you have time dependence in the interior. Because you can see that so one way to check that, one concrete calculation one can do is you can compute the length of the wormhole between these two sides as you move this time forward on both sides. Okay, so this is some particular time, t left and t right, and let's make it the same if you want. The value of TL and TR is the same. Okay, so this is t right. So, and the claim is that as you move TR and TL both forwards, what happens to this, the surface that is connecting them? Sort of I talked to you about the geodesic that is connecting them, right? In higher dimensions, there will be some kind of a surface. So it's very similar to an RT surface actually. So in fact, it is an RT surface, I think. So if you go higher and higher, you will basically see that this length in between basically gets longer and longer. And in fact, in the classical relativity, it can be arbitrarily long. Okay, so there is some kind of a time dependence that is happening here. So the way people interpret that is that the length of the wormhole inside the bulk of in the interior of the black hole has a time dependence, and this length keeps growing and growing. And one can show that this increase in the time, increase in the length of the wormhole is linear in the time that you're moving here. So let's say you start at t equal to 0 here. And then you kept moving. Let me call this TR equals T, and TL is also a T. So the claim is that as you move this T more and more up, so this the surface that is is in the interior that is tracked by it, you can basically measure this distance if you like, and that's it's going to be a distance that keeps increasing. That size is something that keeps increasing linearly with time. Okay, so the wormhole size versus time, and basically it will go like this. And in classical general relativity, it will keep increasing arbitrarily long time. Okay, so Suskind's conjecture is that this object is dual. So this seems like somewhat distinct from what I was saying before, but I will connect it to the typical firewall in a second. Okay, so what Suskind's claim is that this size of the wormhole is capturing the complexity of the state that you're looking at. So complexity is a badly defined idea. I'll tell you roughly what it is, but so the point I want to emphasize, however, is that even after a state thermalizes, its complexity can keep increasing. Okay, so so let me say what that means. So this is the explanation for the never-ending increase of the never-ending increase of the wormhole size in the black hole interior. So with the first observation, in some sense, that there is a in a picture like this, you should not take anything as incidental. You know what I'm saying? That's one of the basic rules about physics. Nothing here is accidental. This is one of the most foundational pictures about black holes. So everything has to be understood. So, and I think that the question that Susskind really took seriously, which seems like a trivial statement almost, is that the interior has time dependence. Okay, so this is supposed to be a thermal state, but there is some notion of time dependence in the interior. So how do you explain that? So that is the question that he wanted to answer, and his answer was that even after some generic high energy state that you start with thermalizes, in the sense that for all small correlation functions, small operators, if you compute correlation functions, they will look thermal. That's what thermalization means. So, but even after that, there will exist a period for which some quantity associated with the state will be linearly increasing. Okay, so that's what he came up with, and he says, I read somewhere or heard somewhere that he thought that, he was puzzled by this for 20 years. So it's an interesting thing to be puzzled. I never thought about it at all. You know what I'm saying? So it's an interesting statement, and so the observation is basically that this quantity keeps increasing with time. Okay, so so the idea is that there is a quantity that you can associate to a state called its complexity, which is what is responsible for the increase in the wormhole size. Okay, so now let's try to define what complexity is. Complexity is not sufficiently well defined as a quantity, but I will just say that very roughly speaking, it is, let's say you pick some particular set of operators or unitary operators. Okay, you start with some base, some some datum state. So there is some state psi, which I call my datum state, and so basically you should think of the Hilbert space as some sphere. Okay, Hilbert space is very close to a sphere, except that it is a unitary sphere rather than an orthogonal sphere. That's the only difference. Okay, so because it's rays in this thing, right? So this is a sphere. So, and the point is that you're starting with some state psi, which I'm calling my psi datum. Okay, so some state psi. So the notion of complexity is basically, let's try to consider some other state psi, and in order to define a notion of complexity, I first have to pick a set of operators which I call my gates. Okay, some set of unitary operators, some small number, but enough so that if I act with those operators enough number of times in various combinations, I can construct any state in the CFT. Sorry, any state in the Hilbert space. Okay, so I choose some unitaries, some UIs, which I call my gates. Okay, and I act with these UIs, and I should be able to construct it. So roughly speaking, complexity is basically the number of given such a set of UI. Let's say some particular set of UI, and they should be small in number, and that's enough actually. You can construct almost every state using XOR gates and things like that. Okay, so if you have a small number of UIs and you act with all of them, you act with them in some way, how do you construct this state psi? Okay, so there will be some, sometimes you may not be able to get to precisely this state if it is a quantum field theory or something, whether there is, states are maybe not exactly, you cannot get to them, then you define some tolerance. You say that, okay, you have to get within this epsilon in the metric of this Hilbert space. Hilbert spaces always have a metric. Okay, it's called the Fibonacci metric. It's basically like the d theta square plus sine square theta d phi square of S2. Okay, generalized to n dimensions, but for unitary spheres. Okay, so there is a notion of a distance in the Hilbert space, and the idea is that you want to act with this chosen UI, these gates, and get to this state within some tolerance, which is also a priori specified. Okay, so and the number of such gates that you need to get to the final state is called the complexity of psi. Note that there are 3 choices I made. I made a datum choice, I made a choice of gates, and I made a choice of tolerance. But the general belief is that for large classes of states that I might be interested in, these choices do not matter. So, but I think that it is, there are many things to be understood here, but this is the belief. Okay, and there are, yeah, that's true. That's true. Yeah, that's true. The minimum number of gates that I need to get to within this tolerance. That's right. So that's basically what I mean by complexity. Okay. So Susskind's claim is that complexity, of course, I mean, this is already note that even in a quantum mechanical system, this is a somewhat ill-defined quantity. Okay, somewhat ill-defined quantity. But the crucial point about complexity, which we have strong evidence for now, is that complexity keeps increasing. So let's say you start with some generic state, some particular state, which is not necessarily thermal, some initial state, which is some prepared state. Okay, and then let it thermalize, which means you just let it evolve. In a strongly coupled system, if you just let it evolve, it will thermalize. So then you will get to a place where correlation functions of small operators in that state will look approximately thermal. But the state will keep evolving even after that, and the complexity of the state can keep increasing even after that. That is the sort of the, maybe surprising, but probably not that surprising, because essentially it's happening because Hilbert space is very huge, and thermal states approximately look like many of them. Okay, so that's roughly the idea. So if you look at that, then the claim is that in many systems, many strongly interacting or chaotic systems, you find that the complexity basically increases linearly with time. Okay, so this is what happens for very long times, even after thermalization. But the point is that after a finite amount of time, like basically time scales of the order e to the s. Okay, so then you find that the complexity saturates. Okay, and essentially that's happening because you have this is basically the states that are here are what are called typical states. Okay, you want the e to the s is not the dimensionality of the Hilbert space, right? So Hilbert space is, if the e to the s, log of the number of states is basically what you define as entropy, if you like. So e to the s is the Hilbert space dimensionality. So at this time, you are basically reached the typical state in the Hilbert space. That's what it means. Okay, so that's the statement. Okay, so the complexity is like kind of an idea that has been around now for again, a few, almost 4, 5, 10 years maybe, 10 years probably. But I mean, at least in the context of black holes, a lot of the work is now, people have done a lot of work on trying to compute complexity, define complexity for field theories, this, that, quantum mechanical systems, etc. But what is, I think, the most interesting application of complexity has still not been explored. And that is basically the fact that what happens to typical states in the context of black holes. Okay, so because here, if so the statement that I made earlier about the possibility or not of firewalls in typical states is closely tied to what happens to the time evolution of the black hole system at very late times, which are e to the s. Okay, so note that in classical general relativity you cannot access it because this will always be increasing, because this wormhole, if the conjecture, this is called the complexity equal to volume conjecture or volume or actions, so any extensive quantity will really do. Any extensive quantity that measures the distance here is kind of enough. Nobody knows it better than that. Okay, so some notion of size of the wormhole should be equal to complexity. This is called the complexity. So action conjecture, volume conjecture, there are many, but none of them are very precise, but none of them matter. The distinctions are, in my opinion, irrelevant. So there might be some subtle thing for which they may be relevant, but I'm just saying that for the purpose that I'm talking about here, the only thing that matters is the fact that the extensivity of the wormhole is increasing linearly with time. Okay, and that's why it is considered to be capturing the complexity of the black hole state. Okay, at late times. So this is in classical general relativity, as I said, because this volume action it keeps on increasing forever, we basically this is that's a problem. That's a problem. It's a failure of classical gravity. So, but on the other hand, in a generic quantum chaotic system, you expect that there will be saturation at some time. Okay, and so at that stage, what happens to the horizon of a black hole is essentially the question of the typicality of the firewall. Typicality of the firewall, or whether there is firewall, etc., etc.
Is it still evolving after the years, or it stopped evolving?
It is still fluctuating. So let me draw a slightly bigger picture. So So it goes like this, then it saturates, and these none of these are to scale, because the time scales are very, very large here. So note that page time is happening somewhere here. So this is much beyond page time. Okay. So page time is roughly speaking order of some power of s. Okay. So this is e to the s, and then there is e to the s, which is basically the Poincare recurrence time. Okay, so this is the time when you expect that after time evolution the system comes back to its original state, close enough. And quantum mechanics also you expect that. Okay. Yeah, so because the system will eventually come back to the original initial state that you prepared, which is of low complexity, right? So if you prepare it somewhere, if you let the system evolve for an double exponentially long time, you expect that it will come back close enough to your original state. Okay, so this is the Poincare recurrence time, but usually, Poincare recurrence time is used in the context of classical physics. But here we are interested in, no, wormhole size, at this point we don't know what happens to wormholes, right? Wormholes is a classical gravity thing. So it's not even clear whether the horizon is smooth after exponential time. Because that's what I was saying, that at e to the s time, now we are in the regime of typical states. So and typical states, it's not clear whether they have firewalls, right? Because of this argument of Marolf-Wall. So there it is not completely clear whether they have firewalls. But if they have firewalls, then already you're not even talking about the interior wormhole volume size, etc. There are various speculations. You can look at, I think Susskind has a paper called Black Holes at X time. Black holes at X time. So, and I think it is a fairly, it's a Susskindian paper, so it's written kind of poetically, but I think it is interesting to read. Yeah, that's right. So I started by motivating this on this thing, but let me call it wormhole size, aka complexity, and only complexity is unambiguously defined after this exponential s time. Okay, so there is, whether there is wormholes after that time, etc., is part of the question of smoothness of the horizon at that time. Okay, so there is a conjecture, one conjecture that at the moment I am sympathetic to, is that so this is again a conjecture due to Susskind, which is that it's only in the complexity increasing phase of evolution that the black hole becomes, the horizon is transparent or smooth. Okay, so only when the evolution is where the complexity is increasing, you have a smooth horizon. So in particular, you will not have smooth horizon here nor here in this fluctuation state, because it's coming down. Right? So this is not that this part of the lecture is now we are in real cutting edge of science, which means it's all speculative. You know what I'm saying? So many of these things could be wrong. But the conjecture, this is, let me call it Susskind's conjecture. But I think he might have, he has refinements of this conjecture also, so I am not 100% sure whether I am representing him correctly. But anyway, so this is one possible conjecture which has some evidence in these non-isometric codes and so on and so forth, which is that, you have, it's only during the exponent, only when complexity is increasing, you have a transparent horizon. Okay, so this is the statement. So this is the claim that Susskind makes. This is a claim, or it's a conjecture, I think, from again 6-7 years ago now. Okay, maybe even a bit more. So, and the idea would be, so then that note that, but that gives a nice picture for the eternal black hole again. So because eternal black hole, so we never discuss the lower half of this picture, right? The lower half of the picture is what is called a white hole. So the white hole is basically something where you are, it's a time reversal of, this evolution that you have here. So in other words, that should capture this part of a fluctuation. Okay, so this is part of one might expect from that. So, and note that the white hole, you cannot go into a white hole because it will be going backward in time. So it's clear that the white hole has a opaque horizon, if you like, by sort of like by causality. Okay, so the question of so in that sense, this this primitive conjecture, but primitive conjecture should be taken very seriously, in my opinion. So so this guy here is basically corresponds to the white hole part, and this guy here corresponds to the black hole part. And this is, I mean, these, of course, you should note that these are all, you should not take this too literally, because these are all, this is not a straight line. This is like some dynamical evolution which is highly complex. I mean, this is sort of a heuristic way of capturing some information. That's, like we don't understand these things well enough. So here anyway, we come back and go up like this. So this is basically sort of like the bifurcate horizon part. Okay, so that's the picture very roughly, and this is a conjecture that it might be good to understand it better. So, any questions?
What happens to the wormhole size?
So there the wormhole size is decreasing, right? Because you're starting from here in some sense, and you're going up. So the wormhole size keeps decreasing until it finally gets to the bifurcated horizon at 0. And then it goes up again and again. So that's that cycle. Okay, so that's the sort of the very heuristic picture. So yeah, so of course, I mean, in some sense, the question of smoothness of typical firewalls is the question of whether general relativity holds in this time scale. Note that this is an exponentially large time scale. We have no understanding of it at all. So it is not impossible that general relativity breaks down. But my general view is that one should be as conservative as possible, but not more. So, and I think that in the exponentially large time scales of that type, it's not very clear what's happening. So I think we need more ideas. Any questions?
So where do we place this site data basically in this picture?
It doesn't really matter. So as I said, choice of side datum, choice of gates, and choice of epsilon, none of these matter for large classes of choices. So there are, so typically what one does in defining complexity is that, as I said, for interacting theories, the ground states, and in general the spectrum itself, the eigenstates, all the eigenstates are highly entangled in the local basis. So you can think of again like, what is it called, Ising model, right? So Ising model has a lot of spins, but the ground state of the Ising model is an entangled state which is built from all these spins together, right? So the one way to define, typically what, you can think of this complexity. It's not completely correct, but it is, you can very roughly think of it as sort of the price for entanglement. So let's say that you take a datum state where it was all the spins in their ground state and all of them are unentangled. Okay, so essentially what I'm saying is that in the case of Ising model, you could take it to be this state. For every lattice site, it is this state. Note that it is not an entangled state. It's a tensor product state on all the spins. But then you could try, so this is your datum state, and then you construct unitaries which basically mix various, multiple, what is it called, pairs of qubits, etc., etc. If you take pairs of qubits and you can entangle them, then basically you can construct any state, right? So you take such states, and then you say that you want to get, you give some tolerance. In the tolerance, this epsilon is basically a measure of distance in the Hilbert space, which is well defined. There is typically when we talk about Hilbert spaces, we only use their linear structure and their unitarity and so on and so forth. But there is also a metric structure you can put on it, which is basically sometimes called Fibonacci-2D metric. Okay, it's really kind of like the sphere metric, but for complex spheres. So, and that metric, you compute the distance, that gives you some epsilon. Let's say I want to be less than epsilon in the Fibonacci-2D metric in this space. Then that gives me a notion of complexity, right? So usually what people do is you're interested in the complexity of, states which are similar to or built from the eigenstates of the system. So, and you are usually trying to define complexity by starting from the unentangled, tensor factors. So that's roughly the idea of how you choose this. But once you make that choice, generally speaking, most choices do not matter. Because especially for chaotic systems, etc., this is like a very, note that we are not trying to extract very sophisticated information. We are just trying to say that this quantity increases linearly and saturates at the typical value. So I don't think this is sufficiently sophisticated to capture, so such a crude definition is enough, very roughly. But of course, if you want to really understand things beyond and, like how exactly, various questions. I mean, all the interesting questions about interior of black hole, what happens to infaller, probably you'll have to make some of these questions more precise, okay? Yeah, so let me conclude with one statement, which is that, note that in the large N limit, so very roughly speaking, this is the region that is accessible when you are in the eternal black hole, okay? So, and note that complexity never saturates in this limit. So the very recent papers of this thing that I already mentioned, it is Leuthäuser and Liu, is suggesting that you should, Leuthäuser and actually the idea was made more clear in some ways by Witten. So Witten, so the claim would very roughly be that you want to hold complexity fixed while complexity of the state fixed while sending n to infinity first. Okay, note that if complexity is fixed and then you are sending n to infinity, now if you do time evolution, complexity will never saturate, because s is going as some power of n, right? So which means that if n has gone to infinity, you are basically always in this slopey part, okay? So that means that according to Susskind's conjecture, it should always have a smooth horizon, okay? And that's consistent with what these guys find, okay? Yeah. No, that's a conjecture. So that's why this is C equal to volume / action conjecture is what is called, but you can check it. So check it means, checking is really not a very meaningful thing, but I spoke too soon. How you can check it means, what it means is that you can check that it is linear. So you can check that the volume or the action or any essentially extensive quantity that you can construct out of the wormhole size increases linearly. So that linear growth of that thing is in principle a check of this conjecture. Okay, that complexity. Of course, it is. You might think that it is a trivial conjecture, but for instance, I did not think that it was a very interesting idea for almost 10 years. But I think this Leuthäuser and Liu paper suddenly have convinced me, even though they don't actually talk about complexity at all. I suddenly got convinced that this is the right picture. But maybe I'm wrong. I don't know. So we'll stop there.